Hello everyone, in this video we will understand the critical section problem and semaphore. Consider a system which consists of n processes from P0 to Pn-1. Each process has a segment of code which is called as the critical section. Each process performs the operations such as changing the common variables, updating a table, writing a file, and so on. The important feature of the system is that when one process is executing in its critical section, no other process is to be allowed to execute in its critical section. This critical section problem designs a protocol for the process such that processes can cooperate. This is done as each process must request the permission to enter its critical section. The section of code implementing the request is the entry section. The critical section is followed by an exit section. The remaining code is the remainder section. Here you can see the structure for the critical section problem. A solution to the critical section problem must satisfy the following three requirements. The first is mutual exclusion, next is progress, and last the bounded waiting. Now we will understand the mutual exclusion. If any process is executing in its critical section, then no other process can be executing in their critical section. Next is progress. If no process is executing in its critical section and some process wish to enter the critical section, then only those processes that are not executing in the remainder section can enter its critical section. And last is bounded waiting. Bound is a limit. Limit is imposed on the number of times that the processes are allowed to enter their critical section. Two approaches are used to handle the critical section in an operating system. The first is preemptive kernel and the next is non-preemptive kernel. A preemptive kernel allows a process to be preempted while it is running in the kernel mode. A non-preemptive kernel does not allow a process running in the kernel mode to be preempted until and unless it exits the kernel mode or it gets blocked. Now I am proceeding with the synchronization hardware. A solution to the critical section problem requires a lock. With this, a process must acquire a lock before entering a critical section and releases the lock when it exits the critical section. Nowadays, a computer system provides a special hardware instruction that tests and modifies the word content or swap the contents of two words atomically. The special instructions are used to solve the critical section problem. We can solve this using the test and set instruction. This instruction is executed atomically. If two test and set instructions are executed simultaneously, they will get executed sequentially in order. So here you can see the definition of test and set instruction and the mutual exclusion implementation using the test and set instruction. If the machine support test and set instruction, mutual exclusion is implemented by declaring a boolean variable lock. This variable is initialized to false. The structure is given here. So now I am proceeding with the compare and swap instruction. Again you can see the definition of compare and swap instruction and the mutual exclusion implementation using the compare and swap instruction. This instruction is operated on three operands. The operand value is set to new value only if the expression pointer value is equals to executed is true. Compare and swap instruction always returns the original value of the variable value. Mutual exclusion is implemented by declaring a global variable lock. It is initialized to 0. The first process that invokes the compare and swap instruction will set lock to 1. Then it will enter the critical section. When a process exits its critical section, it sets the lock back to 0 and thus other process can enter the critical section. This algorithm satisfies the mutual exclusion requirement but not the bounded waiting requirement. So the another algorithm is implemented that satisfies all the critical section requirements. The data structure is given here. It is initialized to false. Now we will prove that the mutual exclusion progress and the bounded waiting requirement is satisfying. So for first mutual exclusion requirement, process can enter the critical section only if either the weighting of I is equals to false or the key is equals to false. The value of key can become false only if the test and set instruction is executed. The variable weighting of I can become false only if another process leave its critical section. Only one weighting of I is set to false. This maintains the mutual exclusion requirement. Now I am proceeding with the progress requirement. The arguments in the mutual exclusion are also used here. Since a process exiting the critical section either sets the lock to false or sets the weighting of J to false. Both allows a waiting process to enter its critical section. And lastly, the bounded waiting requirement. When a process leaves the critical section, it scans the waiting array in a cyclic order. It considers the first process which is in the entry section as the next one to enter the critical section. This was all about the mutual exclusion and the synchronization hardware. So now I am proceeding with the semaphore. Semaphore is an integer variable which is accessed only through two standard atomic operations, that is the wait operation and the signal operation. When one process modifies the semaphore value, no other process can modify it. Here you can see the definition of wait and signal operation. So now I am proceeding. There are two types of semaphores, counting semaphore and binary semaphore. Binary semaphore ranges between 0 and 1. It works same as the mutex lock. Mutex is nothing but the mutual exclusion. Counting semaphore controls the access to the resource instances. It ranges depends on the number of available resource. When the process requires a resource, it performs the wait operation on the semaphore, that is decrementing the count. When a process releases a resource, it performs the signal operation on the semaphore, that is incrementing the count. When the semaphore count reaches 0, this means all resources are used. If any process requires a resource, will be blocked until the semaphore count becomes the greater than 0. With this, the problem of busy waiting may arise. To overcome this, the definition of wait function and the signal function is modified. So here you can see the new definition of wait semaphore and the signal function semaphore operation. When a process executes the wait operation and finds the semaphore value is not positive, then the process waits. Here the process can block itself. The block operation puts the process in a waiting queue. Then the control is transferred to the CPU scheduler, which selects the another process to execute. The blocked process is again started using the wait operation, which changes the process state from waiting to ready. The process is then placed in the ready queue. The block operation suspends the process that it invokes it, and the wake up operation resumes the execution of the blocked process P. This was all about a semaphore.